Okay, again, now we could just calculate the entire EMV of this particular game, the expected utility of this particular game by just doing our usual calculations and adding them up. But remember, we have a shortcut. We can just calculate the EMV for one particular row or one particular column, because all of these are going to be equal since this is a pair that's in Nash equilibrium. So let's just do it for row R1, or I tell you what, let's just do it, since this is the simplest row, let's do it for column C1, okay? Column C1. Now, let's do row. Let's do it row R1, okay? So let's multiply 4. The probability of playing C2, 23 over 24 times 4, the payoff for row, plus 1 over 24 times 20, the payoff for C2 times the probability of C2. That number is going to equal 92 24ths plus 20 24ths, which is going to sum to 112 over 24. And if you reduce this is going to equal 4 2/3. And so the solution to this game is 4 2/3 for row. The expected utility of this game is plus 4 2/3 for row, hence it will be minus 4 2/3 for column. Because again, the expected utility can be calculated by using any of these particular rows, because you know they're equal, they're in equilibrium. And so there's the value for row, minus that will be the value for column. So in this game, row can expect to average a take of 4 2/3 per play of this game, and column can expect to lose 4 2/3. That is playing their optimal strategy. If either of them deviated from playing this mixed strategy to play another strategy, the other could exploit that and row could either raise his or her expected utility if column makes a mistake, or column could lessen his or her expected utility if row makes a mistake and doesn't play his or her part.